So we're now finished developing propositional and predicate logic. And for the second half of the semester, we'll be moving into extensions and variations on this language that have figured importantly in the subsequent developments of logic. Logic is a massive discipline, and so we're only looking at a very few of these, but they're interesting. And they'll also give us a sense of just how much more there is to learn. So we're studying a system of modal logic to begin, and specifically Leibnizian modal logic. So you are already familiar with the distinction between a contingent truth and a necessary truth. Logicians say that these are two different kinds or modes of truth. They're ways of being true. Propositional logic gives us the resources to identify contingent and necessary truths and falsehoods, and we know how to do that. But there are no operators within propositional logic itself that allow us to express this. We can say P, but we cannot say necessarily P. Or put differently, we cannot write in propositional logic a formula that says I am necessarily the case. Modal logic, then, is the extension of classical propositional and predicate logic to different modes of truth. There are actually many different modes of truth. From ethics, for example, you are probably familiar with the distinction between the normative and the descriptive. Descriptive truths, like Melba cheats, are said to be categorically different from normative truths, like Melba ought not to cheat. Deontic logics treat normativity as a distinct mode of truth. Leibnizian modal logic, named after the philosopher Leibniz who conceived it, and if his name rings a bell and you're not a philosophy major, you may also recognize Leibniz as a cookie, and also, more significantly, as the co-inventor of calculus. Leibniz invented calculus more or less at the same time and more or less independently of Isaac Newton. So the reason for considering both possibility and necessity is that they are logically related. For example, a statement like, "It is not necessarily the case that P," is logically equivalent to, "It is possible that not P." Similarly, since we mentioned deontic logic studies obligation and permission, and they're related in much the same way. When we say that it is not obligatory that P, we are saying it is permissible that not P. Obligation is sort of the necessity concept of ethics, and permission is the possibility concept of ethics. Now, you know that predicate logic involves extending propositional logic by the introduction of two new operators, the backwards E and the upside down A. Well, modal logic involves extending classical logic by the introduction of two new operators as well, the square and the diamond. So square P means it is necessary that P. Diamond P means it is possible that P. And notice, just like with the existential and universal operators, when we write these, we do not add brackets. Brackets are still only added when we are concatenating two distinct propositions with one of the binary operators. The relation between possibility and necessity can therefore be expressed like this. Necessary A is logically equivalent to, or if and only if, not possible, not A. Possible A is logically equivalent to, if and only if, not necessarily, not A. So you will, of course, notice immediately an almost uncanny symmetry with the relation between existential operator and the universal operator. For all A, it is logically equivalent to it's not the case that there exists not A, and there exists an A is logically equivalent to it's not the case that for all not A. Those are our quantifier equivalence rules. And those, as we've mentioned before, are an expression of De Morgan's rules for disjunction and conjunction. Now, in ordinary life, we constantly entertain future possibilities, and we also easily acknowledge that past possibilities that did not in fact occur might have occurred. For example, you might say, in all seriousness, if we had left earlier, we wouldn't be caught in this traffic jam. Of course, many of us would say that the possibility of having left earlier is more imaginary than real. Perhaps when we say that something is possible, all we really mean is that it's conceivable. Or maybe that's not what we mean, but maybe that's all that's really the case. Maybe the fact that we can conceive of something or not conceive of it has very little significance for what's possible and what's not. In any case, Leibniz did not think this way. For him, possibilities were real. You may be familiar with Leibniz's claim that this is the best of all possible worlds. This, the one we're living in, is the best of all possible worlds. It was actually satirized by Voltaire in a famous novella called Candide. We live in what we might call the actual world, but Leibniz distinguishes between the actual and the real. Leibniz would speak of the world in which you are not in a traffic jam and arrived on time for the concert as a possible world. For him, all possible worlds are equally real. Possible worlds really exist. When we say we live in the actual world, we are just saying we live in this one, the one where we are in this stupid traffic jam. But the denizens of the other worlds think of their worlds as actual too. The idea that actuality refers only to the world you inhabit, the world you can point to, is called the indexicality of actuality. So, in Leibnizian semantics, we adopt an unanalyzed notion of a possible world, and we say the following: necessarily A is true if and only if A is true in all possible worlds. Possible A is true if and only if A is true in at least one possible world. So if you are philosophically inclined and you are also just really skeptical of the notion of a possible world, then Leibnizian modal logic might strike you as pointless or a futile exercise. On the other hand, if you think possible worlds are cool, then you're really going to be looking forward to seeing how the concept can be made precise and how very precise semantics and proof procedures can be developed. And even if you're skeptical, you might just find that the very fact that this logic is so well developed makes you a little bit less skeptical. So notice that necessity is analyzed as a kind of universal proposition, true in all possible worlds, and possibility is analyzed as a kind of existential proposition, true in at least one possible world. So necessity is kind of an infinite conjunction, and possibility is kind of an infinite disjunction. So there are other interesting and perhaps intuitively implausible metaphysical assumptions that issue from taking the reality of possible worlds seriously. For example, if you say that there's a possible world in which you are married to Morgan rather than Robin, then it implies that you, Morgan, and Robin actually exist in different possible worlds. So as John Knoll, the author of your textbook, points out, you are used to the idea that you are in some sense the same person that existed in the past and will continue to exist in the future. Leibniz asks you to expand your self-concept dramatically. Not only are you the same person over different moments in time, but also over different worlds. And you might say to this, well, if that's the case, why am I not aware of my existence in those worlds? Well, I don't know. Maybe the fact that you can even contemplate their possibility, maybe the fact that you are aware of their existence as possible worlds, means that you are somewhat aware of and your existence in. But remember, the world that you're aware of existing in fully is the actual world, not a possible world. So the idea that the same things can exist in different possible worlds is known as the doctrine of trans-world identity. In terms of our formalism, that means that names refer to the same things in all possible worlds. In other words, since Morgan actually exists in multiple possible worlds, Morgan refers to the same entity in all of these worlds. In possible world semantics, which we'll go on to develop, the technical term for this property is rigid designation. Now, much of our later exposition will be confined to propositional modal logic, but the semantics are better understood if we allow ourselves the resources of predicate logic. You will recall that in predicate logic, we define a universe of discourse which contains names and predicates. All propositions that we can formulate are evaluated as true or false in that universe of discourse. The reality of Leibnizian modal logic is that there are different universes, which we call worlds, and a proposition may be true in one world and yet false in another. So the semantics of modal logic is complicated by the need to speak about a multiplicity of worlds. A model in modal logic will assign to each predicate an extension in each world. Suppose, for example, that there are only 3 worlds, and suppose that we have a multiplicity of objects, which we will designate as in the text by numbers. To see what's going on here, it's important to realize that the numbers here are functioning as objects, not as names. The numbers can be referred to by a name. For example, the object 3 might have the name C. And some objects exist in some worlds but not others, as follows. World 1 contains the objects 1, 2, and 3. World 2 contains the objects 1, 2, 3, and 4, and World 3 contains the objects 2 and 5. Now you notice that I've used the brackets here that are normally associated with the designation of sets, S-E-T-S. And we haven't talked about set theory at all yet in this course. We will be developing set theory later. So for now, we'll just treat these set brackets very casually. It's important for those of you who are thinking very rigorously about this to realize that we are in no way claiming that a world is itself a set. We're just saying that the domain of that can be described as a set of objects. Now, suppose we're interested in specifying which objects have a specific property, G, which we'll interpret as meaning green. Note that numbers, of course, are convenient objects, but it's a little bit of a strange choice, too, since numbers aren't colored and the properties we normally attribute to numbers are typically the same in all possible worlds. Now, suppose further that in world 1, only 2 and 3 are green. We specify what we call a valuation of G at W1 as follows. So the way you read this is that the value of G at W1 is the set containing 2 and 3. Now, I'm introducing this value terminology now while we're studying modal logic, but I don't want you to get the idea that it's only now that it's appropriate. Earlier in the semester, we were just trying to gain or reassert our competence with propositional and predicate logic, so I didn't worry too much about developing the formal basis of the semantics of predicate logic. However, it's worth noting now, before we go on, that if we had done this, we would be using the same kind of terminology. For example, so in predicate logic, we don't have worlds, or you could just say we only have one world, right? And so we don't evaluate predicates relative to a world, but we do evaluate predicates. So rather than say the value of G at world 1, in predicate logic alone, we would just say the value of G. And so if we defined a universe of discourse that had numbers in them, and for some reason we decided to assign properties like green to numbers, we would just say the value of green is 2 and 3, and that would mean that in that universe, 2 and 3 are the only things that are green. So at any rate, here in modal logic, the value of the predicate G at W1 is a set with two members, namely 2 and 3. And all this is telling us is that the only green things in world 1 are 2 and 3. So what we might call a complete valuation for G in a three-world universe might be something like this. The value of G at world 1 is 2 and 3. The value of G at world 2 is 2, 3, and 4. And the value of G at world 3 is nothing. Nothing is green in world 3, the null set. So let's stop briefly and emphasize something. The valuation sign means different things at different times. So when used alone, we're just talking about the Leibnizian model itself in modal logic. When it's applied to a predicate like green, as in the value of G at world 1 is 2 and 3, then V is picking out a set of objects. In the above case, a set of numbers. This set is called the extension of the predicate G. In English, we would say the extension is the set of objects, each of which has the corresponding property. So, for example, the extension of the predicate natural satellite of Earth is a set containing only one object, the moon. The extension of the predicate planets larger than the sun is a set containing 0 objects. When applied to names, V also picks out objects, but since names refer to the same objects across all possible worlds, then the value of a name, V of A, is just one particular object. On the other hand, when V is applied to propositions, then it picks out truth values. So in English, we would say that in this world, the value of the proposition San Francisco is the capital of California is false. That proposition is false in this world. In a particular model, we might ask for the value of a proposition at a particular world. We might say, for example, the value of there exists an xg of x at world 1 is true. Okay? So we talk about the value of predicates, we talk about the value of names, we talk about the value of propositions, and we also use V generally to mean the valuation of an entire model. So it's important to notice that truth and falsity are also now in modal logic relative to worlds, which we can represent with the same formalism. So since the value of G at world 1 is 2, 3, the following proposition is false in world 1 for all x, G of x. And we represent this as follows. The value of for all x, G of x at world 1 is false. The reason for this, of course, is that there are more objects in world 1 than just 2 and 3. So, whereas in predicate logic we could only speak about the truth or falsity of a proposition in a particular model, in modal logic we can only speak of the truth or falsity of a proposition in a possible world or set of worlds within that model. So now we can say what it would be to specify a model in modal logic. This is much more tedious in modal predicate logic than in propositional logic. And we'll just glance at what would be required in modal predicate logic, and then we'll switch to modal propositional logic to work with something a bit simpler. So a Leibnizian model, V, for a set of formulas can be stated in 3 conditions. Now the first 2 are simple. First, we have a non-empty set W of V, which means the worlds of V of objects. So we have a set of worlds, and it has to contain at least one world. And for each world, W, in WV, a non-empty set, DW, which is the domain of that world. So this is actually very important. In Leibnizian modal logic, we don't have empty universes, and we also don't have empty worlds. This actually means something rather controversial, as we'll see later. Philosophically controversial, not logically controversial, which is the claim that something exists is actually a necessary truth. That strikes many philosophers as weird because empiricist-minded people are inclined to believe that whether or not something exists shouldn't be a matter of necessity, but that it should be a matter of contingency. On the other hand, the idea of an empty world is also kind of weird. If a world is empty, after all, what makes it a world at all? Anyway, in other words, a set of worlds and a set of objects both of which are non-empty, are constitutive of, or partly constitutive of, a Leibnizian model. Now, the third condition's a little longer, and we're just going to paraphrase it here. It's provided in much greater detail in your textbook. The first condition says that for any name letter A, and note that I'm using the script form here again, so A refers to any name letter, not some particular name A. So for any name letter A, the value of A is an object in at least one world of V. So that basically just tells us is that if we have a name, it has to be the name of something somewhere. The second condition tells us that for any capital sentence letter P, so this would be from propositional logic, right? The value of P, and here of course we're talking about a truth value, at every world W is either true or false, but not both. So in other words, every propositional logic letter has a truth value, and it has only one. Now, if on the other hand, condition 3, if P is a one-place predicate, then for any world, the value of P at that world is a set of objects. And here there is no requirement that it not be the null set. In other words, you can have a predicate that no object in any world actually has, or to put more precisely, for which no object in any world is the value. And then the fourth condition says if P is an n-place predicate, then for any world, the value of P at W is a set of n tuples of objects. So, for example, if P were a two-place predicate, say penetrates, then the value of P at any world isn't just one object, but ordered pairs of objects, like A, B, or 1, 2, etc. So conditions 1, 2, and 3 may be summarized as follows. A Leibnizian model for a set of formulas is a set of worlds, a set of objects populating those worlds, both of which are non-empty, and an assignment of valuations to objects, propositional letters, and predicates. Now, that third condition entails a very long list of valuation rules for every type of atomic and molecular formula that can be stated in modal logic. We won't go over them all here, it's in the book, but it's important to know what they are saying. So the first rule, for example, is if P is a one-place predicate and A is a name whose extension, the value of A, is the domain of that world, the domain of a world, W, then the value of P, A at W is true if and only if the value of A is an element of the value of P at W. And the value of PA at W is false if and only if the value of A is not an element of the value of the value of P at W. Now, once again here, we've snuck some set theoretic terminology, the idea of being an element of, or what we sometimes call a member, and we'll just use this intuitively for now. I'm sure you've encountered the relation before. Later on, when we develop set theory as an extension of predicate logic, we'll have an explicit incorporation of this relation into the language of predicate logic. But for now, we're just using it meta-theoretically to describe the evaluation rule. Now, you really want to take some time to understand this and also sort of to appreciate just how elegant it is. So if you just think about the first one, what it means for something to be true, right? It tells us that the value of an atomic formula like P of A, say A is pure at a world, is true, right? So P of A is true if and only if the value of A, and what is the value of A? Well, value of A is, remember, a particular object. A refers to a particular object. So if the value is an element or belongs to the value of the predicate at that world. So P of A is true at a world if the object that A refers to belongs to that set of objects that we define as the value of the predicate. So we're able to say what it means to be true and in terms of the relation of being an element or being a member of the value of A and the value of the predicate. So this way of talking was a really, really important innovation in the history of formal logic. So the valuation rules that are most interesting to us are the ones that specify the truth conditions of formulas involving the modal operators. They're not very complicated, and we'll just state them here in English as follows. The rules are numbers 11 and 12 in the text. So for any proposition A in a model V, specifying a set of worlds, WV, necessarily A, box A, is true in a world if and only if A is true in every world. So when we say that necessarily A is true, we're saying that in every single world A is true. So when we say that necessarily A is false, not necessarily A, right? That would be not necessarily A is true. Necessarily A is false in a world if and only if A is not true for some world. So it's not the case that the value of A is T at some world. And then diamond A, possible A, is true in a world if and only if A is true in some world, and diamond A is false in a world if and only if A is not true for every world. And that's a little ambiguous. What we mean here is that in every single world, A is not true. This is actually pretty intuitive. This is really how we use the concepts of possibility and necessity if we get used to talking about possible worlds. So if I say it's possible that my mother is a frog, I'm saying that there actually is some world in which my mother is a frog. If I say it's not possible that my mother is a frog, I'm saying there is actually no possible world in which my mother is a frog. If I say it's necessarily the case that my mother is a frog, I'm saying in every single world my mother is a frog. If I'm saying it's not necessarily the case that my mother is a frog, I'm saying there's at least one possible world in which my mother is not a frog. So it's worth emphasizing here that even though the truth conditions of a modally quantified proposition, like necessary f of A, depend on the truth conditions of f of A in every possible world, the truth of necessary f of A, the modally quantified proposition, is still relative to a particular world. In other words, any woof in modal logic semantics must be expressed from the perspective of a particular world. Hence, we cannot speak meaningfully, for example, of the truth or falsity of f of A simply. We can only speak of the truth or falsity of f of A at world 1 or at world 2, etc. So it's also important to note that not every predicate logic woof in Leibnizian modal logic will end up having a determinate value. The reason for this is that a predicate logic formulas can only be judged true or false if the name employed refers to an object in that world. So, for example, if we're asked to evaluate the value, the truth value of f of a at W3, and a does not belong to W3, the semantics doesn't give us an answer to that question because the rules are explicit that a has to be an element of the domain of the world identified. Now, this sort of shortcoming or weakness in Leibnizian modal logic is one of the reasons for developing a system known as free logic, and we'll be talking about that one next week. Okay, so to repeat, if the object does not exist in that world, then the wolf cannot be judged true or false by reference to our semantics. But this is not the same thing as saying that the wolf has no truth value. It's just that the rules are silent on the question. And this is actually why, when specifying the valuation rules for the falsity of modally quantified formulas, we speak of the corresponding non-modally quantified formulas as being not true rather than false. For example, the value of necessarily FA at some world is F, if and only if the value of FA at that world is not true for some world. That's what that valuation rule we looked at said. We say not true rather than F because we want it is necessarily the case that Alvin is funny to be false if and only if it is not true that in every single world Alvin is funny. If Alvin does not exist at a world, FA has no truth value. So while it is not the case that FA is false, it is the case that FA is not true. So this is captured in the very first valuation rule, which states that given any Leibnizian valuation V for any world W in the worlds of V, if P is a one-place predicate and A is a name whose extension, the value of A, is an element of DW. And remember, the value of A is an element of DW just means that A names an object in that world. So if we read it that way, if P is a one-place predicate and A is a name of an object in some world, then the value P of A at W is true if and only if the value of A is an element of the value of P at W, which remember is just a way of saying that A in fact has that property. And the value of PA at W is false if and only if the value of A is not an element of the value of P at W. The critical stipulation here is that the value of A is an element of DW, which means that the object designated by the name A exists within the specified world. The semantics tell us the truth value if the value of A is an element of DW, but not otherwise. And as I mentioned, we'll soon see that a non-classical system called free logic is an alternative that escapes this restriction. So again, it can be useful to compare this situation to regular non-modal predicate logic. In the past, if we were to construct a model, then every predicate logic wolf would be either true or false in the model, so long as it uses predicates and names that have been given an interpretation in the model. In fact, in regular predicate logic, we can define a universe like all living female physicists, but we only specifically name a few of them in the model. In this case, we are still able to say that something is over 6 feet tall is true in the model if an unnamed female physicist happens to have that property. But any predicate logic formula that specifically employs a name or a predicate not interpreted in the model will have no truth value. It would be like all mimsy were the borogoves, a meaningless but perfectly grammatical sentence. In modal predicate logic, to have a truth value, it is not enough that the predicate and name be interpreted in the model, since every woof in modal predicate logic is only true or false in a particular world in that model. Then the named object must actually occur in the world in question. Now, if we confine ourselves to propositional logic, where only capital sentence letters are formulas, and which has no capacity to refer to specific objects in the domain of a world, semantics are a great deal simpler to state. A Leibnizian model V for a set of formulas in modal propositional logic consists of a non-empty set WV of objects called the worlds of V, and for each sentence letter P in that set of formulas and each world W in WV, an extension, the value of P at W consisting of true or false, but not both. In other words, the model just has to tell us whether P is true or false in the model. So, less formally, a Leibnizian model for a set of worlds in propositional logic consists of a set of worlds, an assignment of either true or false to every proposition that can be formulated within each world. As you know, the semantics of classical propositional logic is supplied by truth tables, and a more complicated version of this can be done in modal propositional logic. So if we say that the worlds of V, the set of worlds in the model V, is the set containing world 1, world 2, world 3, and world 4, we can provide truth conditions for propositions P and Q in different worlds as follows. So for the worlds of V equals the set containing world 1, world 2, world 3, and world 4, and propositions P and Q in V, and I won't read these all out, but we could say that the value of P at world 1 is true, the value of P at world 2 is true, we could say the value of Q at world 1 is false, we can say whatever we like, but the point is that it has to be explicit in the model. So these truth values have just been assigned randomly in accord with the standard semantics for the operators and the rule explicitly specifying the truth value of the conditional. We can infer from this that, say, the value of if P then Q at world 2 is true, and that's simply because both P and Q are true at world 2. When a Leibnizian model has been fully specified, it becomes possible to prove things about the model. These are meta-theoretical proofs. This means that we're not yet using a system of derivation for modal logic, as, for example, we develop for regular propositional and predicate logic. That's actually our next task. Rather, we are just using English and the valuation rules specified in the model. So consider the proposition necessarily if P then Q. This says that it is necessarily the case that if P then Q. What does that mean exactly? Well, recall that in propositional logic, if P then Q is only false when P is true and Q is false. So, for example, it is true whenever P and Q are both true. This is something that most of us assented to readily, but in reality, it is no more intuitive to assign true here than to assign true when the antecedent condition is false. Why? Well, in English, when we state a proposition of the form if P then Q, we're usually saying that Q, in some sense, depends on the truth of P. Suppose you learn that Peter likes pickles. Later, you learn that Quinn is into quilting. Would you say that this proves that if Peter likes pickles, then Quinn is a quilter? Well, that's a very strange inference. Most people would say, no, these are both true, but one does not entail the other, or at least we have no reason for asserting that. They really have nothing to do with each other. Now, you'll recall that in propositional logic, we sidestep all of these arguments by saying that the material conditional, the arrow, in propositional logic is not meant to capture what is often called the indicative conditional in English. But modal logic is at least partly developed to deal with this, and now we're in a little bit of a position to see how. In the case of the conditional, the basic idea is that necessarily, if P then Q, gets us a little bit closer to the meaning of the indicative conditional. But how? Well, recall that according to the valuation rules for Leibnizian modal logic, necessary P is true if and only if P is true in all the worlds specified in a model. Hence, necessarily if P then Q will be true if and only if P then Q is true in all of the worlds. So this gets us a lot closer to the meaning of the indicative conditional, because if you know that in every possible world in which Peter likes pickles, Quinn is a quilter, then the fact that Peter likes pickles does entail that Quinn is a quilter. So now reconsider the four-world Leibnizian propositional logic model V we specified earlier. Is it the case that necessarily if P then Q? Clearly the answer is no, because if P then Q is true only in worlds 2 and 3. Now we need to be careful when we're doing proofs like this. Contrary to what I just suggested, we cannot ask simply whether necessarily if P then Q is true in the model. What we can ask is whether necessarily if P then Q is true or false in a particular model, a particular world of that model, such as W3. We can also ask whether it's true or false in every world of that model, and we can ask whether it's true or false in some world of that model. Of course, because of the nature of necessity, these all have the same answer in this case. So the correct way to do this sort of proof is as follows. Prove that the value of the necessarily if P then Q at W2 is false in the specified model. And we're using this model I've got up here at the right. So the full explicit proof would read, the value of necessarily if P then Q at world 2 is false if and only if the value of if P then Q is false in at least one world, Wn of Wv. And here we would cite a rule for this, and in this case in the text it's Rule 11. Now remember, because we're operating in propositional, where everything has a determinate truth value, we can say that the value of if P then Q equals false rather than the value of if P then Q is not identical to true, which is what we have to do when we're dealing with predicate logic, modal predicate logic. Okay, so the value of if P then Q is false in world 1, referencing now the model, since in world 1 P is true and Q is false. And that is given to us by another rule, Rule 7 in the text. Therefore, the value of necessarily if P then Q at world 2 is false. Now, I'm not going to be asking you to produce semantic proofs of this kind, but it is important to know how they are done and that they can be done. So alternatively, we can also show that necessarily if P then Q is false in every possible world like this. Let W be any world W, not just some world, such that W is an element of the worlds of V. Then the value of necessarily if P then Q is false in W if and only if the value of if P then Q is false for some world in WV. So the value of if P then Q is false in world 1, since in world 1 P is true and Q is false, rule 7, therefore necessarily if P then Q is false in every world in V. So because the truth and falsity of modally quantified propositions depend on what is going on in other worlds, we also have to modify our understanding of some of our other metatheoretic concepts that relate to truth and falsity. Now these are listed on page 232 of the text. They're fairly straightforward and essentially just require adding reference to all possible worlds or some possible worlds in the obvious way. For example, a formula is valid if and only if it is true in all worlds on all of its valuations. And this brings out an important point about the nature of necessity. In modal logic, when we say necessarily A, we are not claiming that A is valid. In other words, we are not saying that A is a tautology. So, in modal logic, we have developed an analysis of the concept of necessity that is completely different from the concept of necessity that we use when we say that something is a necessary truth, right? So necessarily A is true in a world if and only if A is true in all worlds of the model. So this sense of necessity is model specific. Necessarily A may be true in one model, but not in another. But A is a necessary truth in the sense of being a tautology or a validity in modal logic if and only if A is true in every world of every model. So that's a very important distinction to maintain. Tautologies or validities all end up being necessities in the modal logic sense, but not all necessities in the modal logic sense end up being tautologies or validities in the truth functional sense. So the other propositions or definitions that we have to tweak a little bit for modal logic purposes: a formula is consistent if and only if it is true in at least one world on at least one valuation. The formula is inconsistent if and only if it is not true in any world on any of its valuations. The formula is contingent if and only if there's a valuation on which it is true in some world and a valuation on which it is false in some world. Section 11.3 in the text is a brief philosophical digression regarding logical and naturalistic restrictions on the specification of models. For example, since our world exists, we can safely say it is a possible world. In our world, there are many sorts of objects and many sorts of properties we can meaningfully ascribe to these objects. It is central to Leibnizian modal logic that you exist in multiple possible worlds. That, you'll remember, is the doctrine of trans-world identity. But Leibnizian logic does not decide the question whether there is a possible world in which you have different parents or in which you are a salamander. It is tempting to think that we know what is logically possible and what is not by reference to what we find conceivable or how we currently use terms. However, it is not true. There are all sorts of things that people regarded as logically impossible in the past that turn out not only to be possible, but to be actual, that is to say, true in our world. A moving earth, an evolving species, a number less than 0, a sighted blind person, a divisible atom, an actual infinity, a multiplicity of universes, are all examples of now important ideas once thought to be logically